Hello everyone. Today we are diving into one of the most iconic problems in fluid mechanics, which is flow past the sphere. This topic is fundamental because it combines theoretical elegance with practical relevance. Let's begin by asking why study flow past the sphere. Imagine this scenario where a raindrop, which can be approximated as a small sphere, falling through the air experiences drag forces that slow its descent. A blood cell, roughly spherical in shape, moving through a capillary, encounters viscous forces that dominate its motion. These are just few examples where understanding the flow past a spherical object is critical. Understanding this flow is key to solving engineering problems and explaining natural phenomena. By the end of this lecture, we will understand how the Reynolds number dictates behavior and why this is important in both engineering and nature. But first, to guide our discussion, here are three key questions we shall address now.
How do viscous and pressure forces compete around a sphere?
What happens is this interplay between pressure and viscous forces determines drag, which influences how objects move through fluid. For instance, when a sphere moves through a fluid, viscous forces act to slow it down, while pressure forces can either push it forward or backward depending upon the flow conditions.
Why does flow separate and how does this affect drag on sphere?
Flow separation arises due to adverse pressure gradient, which are rising pressure in the flow direction combined with viscous effect. Flow separation leads to weak formation behind the sphere, increasing drag significantly at higher velocities. This is particularly important for the sphere because the shape of the wake can vary greatly with the Reynolds number.
What happens when we scale from microscopic spheres to large spheres like cannonballs?
The behavior of fluid changes dramatically with size and speed due to varying Reynolds number. For small spheres like dust particles, flow is smooth and viscous. On the other hand, for large spheres like cannonballs, flow is turbulent and chaotic. Now, concluding this, let's introduce the Reynolds number, which is denoted as RE. This dimensionless quantity is central to fluid mechanics because it tells us whether inertia or viscous dominates in a given flow scenario around a sphere. The formula for Reynolds number is given as Re equal to rho into d into V by mu, where rho is the fluid density, V is the velocity of the fluid relative to the sphere, d is the diameter of the sphere, mu is the dynamic viscosity of the fluid. The Reynolds number essentially compares inertial forces like momentum to viscous forces like friction around the sphere. It acts as a switch that determines whether fluid behaves smoothly or chaotically around a sphere. Now let us understand how flow regime at different Reynolds number act around a sphere. Let us begin with low Reynolds number with Re less than 10. At low Reynolds number, think of it as a microscopic scale or a very slow motion in which the fluid behaves like honey flowing around a marble. Viscous forces dominate here and inertia is negligible. This regime is called creeping flow, which is characterized by smooth and symmetric streamlines wrapping tightly around the sphere. There is no turbulence or wake formation here. Instead, drag arises purely from viscous friction. Now let us come to high Reynolds number, with RE greater than 1000. Imagine air rushing past a speeding car or a cannonball fired through water. Here, inertia dominates over viscosity, and the flow becomes chaotic. Turbulence develops behind the sphere as streamlines detach from its surface and forms a wake. This phenomena increases drag significantly due to pressure differences between the front and rear of the sphere. In this part of video, we are diving into fascinating world of fluid mechanics. Our focus is understanding the flow of fluid past the sphere. This phenomena is governed by some of the most fundamental equations in physics, which is the Navier-Stokes equations. These equations not only describe fluid motion but also serves as the backbone for much of what we understand about how air, water, and other fluids behave under different conditions. Now, let's begin by introducing the governing equations of fluid motion, the Navier-Stokes equation. These equations were developed by two brilliant scientists, Claude Louis Navier and George Gabriel Stokes, in the 19th century. Their work forms the foundation of fluid dynamics, helping us understand how fluid moves and how different forces affect that motion. The journal form of Navier-Stokes equation looks like this. Now, let's break this down and see what each terms represent. Here, rho, this is the fluid density, which tells us how much mass is packed into a given volume of fluid. V, this is the velocity vector field of the fluid. It describes how the velocity of the fluid particle varies across space and time. P, this term represents pressure in this fluid, which influences how fluid moves and deforms. Mu is the dynamic viscosity. This is the measure of a fluid resistance to the flow. A higher viscosity means the fluid flows more slowly and resists motion. F is external body forces such as gravity which affect the movement of the fluid. These equations are derived from Newton's second law of motion but applied to a small element of fluid. They are applicable to Newtonian fluids like water or air, where the relationship between stress and strain is linear. However, these equations are not just simple, straightforward formulas. They are nonlinear partial differential equations, which means solving them can be extremely challenging, especially when the flow becomes complex. So, why are the Navier-Stokes equations so difficult to solve? The main challenge comes from the nonlinearity of the equations, specifically the convective terms. These terms describe how the fluid velocity changes along its own path, making the equations incredibly sensitive to small changes in initial conditions. This is one of the main causes of turbulence, which leads to chaotic and unpredictable fluid behavior. like the formation of vortices. But not all fluid flows are turbulent. In certain cases, where the fluid is slow or the flow is slow, the viscous forces dominate over inertial forces, where we can simplify the Navier-Stokes equations. This happens when the Reynolds number is low. When Reynolds number is less than 1, we can see a regime known as Stokes flow or creeping flow. One of the major breakthroughs in fluid dynamics came in 1851 when George Stokes simplified the Navier-Stokes equation for low Reynolds number flow. In this regime, the fluid moves slowly and the effects of viscosity dominate. This flow is smooth without any turbulence or wake formation. Stokes made two key assumptions that allowed him to derive a simple solution for the flow around a sphere. First, he assumed that the sphere moves slowly through the fluid. This means there is no turbulence or large-scale fluid motion behind the sphere, just a steady laminar flow. Second, he applied the no-slip boundary condition. The fluid at the surface of the sphere moves at the same velocity as the sphere itself. This is a fundamental assumption in fluid dynamics and tells us that the fluid is effectively stuck to the surface of the object. By making these assumptions, Stokes was able to simplify the Navier-Stokes equation significantly. The result is linear relationship between the drag force on the sphere and its velocity relative to the fluid. Following is the Stokes equation. In this formula, Fd is the drag force acting on the sphere, r is the radius of the sphere, and u is the relative velocity between the sphere and the fluid. This simple yet powerful equation tells us that the drag force increases linearly with the velocity of the sphere, which is quite different from what we observe in higher Reynolds number flow, where drag force often increases on non-linearity. This result was groundbreaking and has application in a wide range of real-world scenarios, from filtering wastewater to understanding the momentum of plankton in oceans. Stokes' law helps us to model and predict how small objects move through viscous fluid. It's especially important in fields like bioengineering and even in aerospace engineering. While Stokes' law applies to a specific idealized case, the insights it provides are invaluable, especially when we consider the challenges posed by more complex fluid flows. The Navier-Stokes equations are the foundation of fluid dynamics, describing how fluids move under the influence of various forces. While these equations are powerful, their non-linearity presents significant challenges. But by applying simplifying assumptions, as in the case of Stokes' law, we can derive important results that apply to a wide range of practical situations.